connected. So I'll give you the name of that in just a second, but we'll pause for a minute on my first slide, just let you guys see that. I renamed it so that we wouldn't get confused, but theoretical fluid mechanics is still in the name. So why don't I go ahead and start sharing here? I'll show you what that looks like. Weird. Okay. So right here. Sounds like somebody needs to mute. So right here, this is it's called now 2021 CVEN 3313 Theoretical Fluid Mechanics. Before, I think we had just called it Theoretical Fluid Mechanics, so I added the other information at the front so we wouldn't get confused. When I unlinked the course, I then retired it or something. So hopefully that's not an option anymore, but that you can go in and find this one. So please do that. Take a minute to let you guys do that, because we will have a couple of questions today with the iClicker. Okay.
Yeah, give me some.
Give you guys a second to do that.
I'm personally struggling to find it. I don't know if that's just me, but.
So that's through, you are doing that through Reef. Let me move this, sorry.
Yeah, I am.
Let's see. So Natalie, you typed in fluid, did you find it? Oh, okay, Lauren says she looked up mechanics and it was at the bottom.
Yeah, it's the 2021 one. I just typed in fluid and it was right there.
Yeah, maybe it works to find my name. Sounds like 2021 CVEN will find it too. So you can just search on part of this, it sounds like. Where? So this is, you can click the link from Canvas to do this through a web browser, I believe. Or you can try to do it if you have the app on your computer, the iClicker app, or Reef app, rather. Okay, I'll let people keep working through that. Let me just do a little general introduction here. We're going to keep talking about fluid statics, and I want to talk about pressure distribution some more today. And in particular, we're going to spend some time looking at a very specific example, but one that civil engineers come across a lot, which is pictured on the right here. Does anybody know what dam this is? It's a big piece of concrete in the middle of a desert, not unlike many other dams. But does anybody know what this one is by chance?
The Hoover Dam?
Not Hoover, but we will get to Hoover. Glen Canyon. There you go. Luke got it. So this one's Glen Canyon. So it backs up Lake Powell, and then I don't know, what is it? Is it about 300 miles, 250 miles, something like that downstream? Is Hoover, and we'll talk about Hoover in more detail later today. But it doesn't look all that different. I mean, you're right. This is in both of these cases. One of the things you'll see is that to build this dam, the idea was let's find a canyon where you can fill up a narrow cross section, right, with concrete to try to back up water beyond it. And what we're going to talk about today is a little bit of the hydrostatic pressure distribution on the back of those dams. All right. So we'll get to that in detail. And part of the reason I'm belaboring this is that this is really, really important. As we move forward, if you understand these concepts well, you won't get as confused when we start changing things like geometry of the hydrostatic pressure, like on a gate or something like that. All right. And that's where we're going in a couple of weeks. All right. Or actually after manometry. So coming right up. So grade one homework one grades are posted. We have the TAs, Alexia and Emma, did a great job of finally pulling those together. In general, we will try to have those done less than a week from when everything is submitted. This time took a little longer for two reasons. One, it was all hand grading, or grading every individual problem, and then secondly, we were kind of working on our approach to how we set up our rubrics for grading and so forth. If you have questions about your grades or the way things worked, and two more things. One is, when you go in to look at your grade, you should be able to pull up your assignment and see comments, and those comments should give you some understanding of why you lost any points if you did. Then secondly, I know that you have the opportunity to also put in comments. We have no way to find those unless we go look for them. So that's not a great way to communicate. So when I cut myself off of saying it earlier is, if you lost any points and you have questions and the comments don't explain well enough, please reach out to the two TAs. You can do it during their office hours, or you can do it separately via email to try to figure out, get some explanation if you need it. So let's see, aside from that, homework 3 should come available. I think I set it up for 12:50. It might be 1 p.m., but by the time we're done with class today, homework 3 should be available to you. The other thing that I've figured out is I'm having a little trouble continuing to make the Wiley Plus problems and the assignments available in that homework module that I have on the homepage. So I just set up a little announcement there that says all homework assignments will now be in the assignments tab. So apologies. I thought I was being clever by kind of putting that stuff on the homepage for you, but it looks like we'll have to go to assignments now. So sorry about that. But in any event, we'll try to keep it all consistent in one place. And I thought that was more important than trying to provide something on the homepage that would be mixed or wouldn't have all of the pieces to each homework. Okay, with that, in case anybody just joined, just note this right here, that I have reset the class name and got rid of the old one in iClicker and Reef. And the idea here is that by the time we're done, hopefully your participation grades will be getting auto updated into the Canvas gradebook. And that's what we're aiming for. All right. Okay, any questions before we get going? Okay, then off we'll go. All righty. Okay, so just a quick review of what we did yesterday Tuesday, without getting into the nitty gritty. We won't rederive all of the equations, but those derivations are really important for proving a couple of bottom lines here. And the bottom lines that are really important are the fact that we found that there is no hydrostatic pressure distribution in the X or Y direction, and that there is in the vertical direction. Okay, so remember, we started with this wedge, and as we went through, these were forces that were resulting from pressures acting on each of the 5 faces of this wedge. And we are actually only showing 3 of them plus the weight. And we have left out the 2 forces resulting from pressures that are acting in the X direction, positive and negative, because we reasoned that they would cancel each other out. And so after we went through the process of doing the force balances in the Z and Y directions, we were able to come up with some very important conclusions, okay? And by the way, these are conclusions that would be a little bit tougher to find if we hadn't used this wedge. Part of the reason that this works out so well is that we have our pressure direction is always normal to the face of our body. In this case, this wedge is our body that we're looking at. And so the pressure is always going to be acting normal to that face. And because this happens to be at a slope, we end up with Z and Y components of the resultant pressure. And so we could then work through the y component of this pressure force interacting or being offset by this horizontal pressure force also in the y direction. And then from a vertical perspective, we had a vertical component of this pressure force acting on the top face, the weight, obviously, and the pressure force acting from underneath, okay? So one thing that's important to note that I hope you're picking up on here is that even if we, jump into a swimming pool, or I think on Tuesday I had a picture of a pickup truck underwater, right? Pressure doesn't necessarily care about gravity to work, right? Certainly gravity and the direction of the gravitational force is important for weight, but the offset of that, we can have these pressures acting upwards. That doesn't matter which direction it's going. It's always just going to be orthogonal or normal to the face of the object that is submerged, right? And on all faces. In this case, we've tried to idealize that by only looking at 3 of the 5 faces of this particular object. So remember also that the resultant forces from these pressures on each one of these faces were simply the pressure value. So those are the small p's for these 3, this py, pz, and ps. So those 3 p's that are shown here for the 3 solid line arrows, and then multiplied by the area of those faces. And we've made them simple here so that they are rectangular, right? So we have a delta x and a delta z. Those are simply delta s, delta s, delta x, delta s, delta x wide, delta s long. We could say for that face, and delta x wide and delta z high on this face, etc. And then the only other thing was, hopefully you're starting to recognize that it's fairly easy to figure out the weight of different objects when we have a specific a specific weight and the volume. Right. If we can figure out the volume of shapes, we can probably figure out that weight force pretty easily. Okay. And then we said that this led to Pascal's law for a static fluid, which is that pressures at a point in a static fluid are independent of direction. So that's a different way of saying, hey, even underneath the block or underneath the pickup truck, there is pressure acting upwards underneath that. It doesn't matter that gravity is acting in the opposite direction. Pressure is in a sense independent of gravity because it acts in all directions, right? So a pressure at this point, this depth would have P's sort of acting, and this is a small circle, right? And so we have P's acting in all directions on that, sort of normal to that small circle. Same thing over here, and these might be 2 different P's because they might be at 2 different depths, so 2 different sets of pressures. But there's even pressure distributed across this small circle in this case.
Professor?
Yes,
Could you go back a slide really quick?
this one.
Yeah, so on the Y plane, coming into the block and out of the block towards us and away from us, do those
The XY plane.
right, do those cancel?
Oh yeah, the pressure forces acting in the X direction we ignored because they were going to be equal to each other, the pressures, and they were going to be acting on identical faces. So we assumed, so rather than make this busier and harder to read, we are canceling those out. So we're just working in the Z and Y direction for this case. Yeah, does that make sense? Does that answer your question?
Yeah, so like if you had a full cube, the only force that you would really have to worry about is the weight force, right? Because every other pressure force would cancel?
Yes, in a way, right. Because you end up with that, yes and no. Let me get to that. We'll get to that in a couple slides in my summary, and I'll tell you why that's not quite true.
Okay.
But yes, in the X and Y directions here, they should cancel out if this was a cube.
Okay.
Okay, so of course pressures can vary from point to point, but at a point the pressure should be acting on all faces the same amount. Okay, so now Christian, coming back to your question here a little bit. Now, instead of taking an object and putting it in the fluid, let's take a fluid element, and it's infinitesimally small, or it's got dimensions of delta z, delta y, delta x, and it's a cube. So let's just say whether they were equal to each other or not, in this horizontal direction, so we've chosen the y direction here, we have a face that is delta x wide and delta z tall, and the same dimensions occur on this side as well. These two pressures, because they're acting normal to the face on both faces all around this cube, are identical in value. We have accounted for a pressure gradient in the y direction if it existed. But because we're dealing with hydrostatic pressure, this pressure difference is essentially going to be zero, as is this one. So these two pressures will offset each other. That is, they are even in magnitude. So in the x and the y direction, that will be the case. And so some of the forces in the the y direction equals zero. dp dy, the pressure gradient in the y direction, is zero. The sum of the forces in the x, when we worked through that set of equations, we did y, but in any event, we would end up with dp dx or del p del x, or the pressure change in the x direction also being equal to zero. Now, getting back to your question, Christian, when we do this in the z direction, it's a little bit different. And you are correct that we have to account for another force, and that's weight. However, there's one other small thing that's happening here, and that is that the pressure that is reaching this face at the top of this cube is actually different than the pressure acting on the bottom. And the only reason is that they are separated by some amount delta z, because pressure changes with depth. So if this small cube, and we're just talking about a cube of of the fluid itself, because we have that pressure differential, and let's say it's an inch tall, well, there's a lower amount of pressure on the top than there is coming up from the bottom. So that's one imbalance that occurs, but the weight acts in the opposite direction, right? The weight, so this will be, this total force acting on top from pressure is going to be smaller because it's shallower than this pressure acting on the bottom from below in the opposite direction. So what that means is you'll have a net upward force, but that's countered by this weight. Okay, so the difference between these is countered by, or is offset by, the weight acting in the downward direction. Okay, and so when we went through that exercise of putting all of these terms together and actually doing the force balance, we found that dp dz, or the change in pressure in the z direction, is not equal to zero. And in this case, it's going to be equal to minus gamma. So one thing to note is this is constant, so that's not a bad thing. But the other thing to note is that it is not zero, okay?
Professor, I had a question.
Yeah.
So if the top of the cube had a bit of air in it, would it make a big difference?
Well, this cube is actually one that is of the fluid itself. So it's not an object. If it was an object that was submerged in the water and it had air, it would be a buoyancy issue. So that would be a little bit different. And we'll talk about that, I think, week after next. So we will get to buoyancy. So, yeah, good question. That would offset the weight a bit as well. Yeah. Okay. So with this relationship, del P del Z is equal to minus gamma, we could take that a step further and say, okay, well, let's say I have 2 points of interest. They're both under a fluid, a free surface of some fluid. Point 2 is high, or elevated above point 1, right? And if I create a datum that is down here, then point 1 is some Z1 high, right? It has an elevation of Z1. And there's going to be some pressure P1 related to how far down it is below the free surface. Similarly, at P2 or point number 2, we will have some other P2 because it's at a different depth below the free surface, and it will have some elevation Z2 above our datum, all right? So when we went through this, we said from the previous slide, we changed it from a partial differential to dP dz is equal to minus gamma. And what we could do then is rearrange this to say that the change in pressure is equal to minus gamma times the change in elevation, all right? And so what that further led us to was to say if we integrate these, this equation on both sides, one with respect to pressure and the other with respect to elevation, then we work out this formal integration. We end up with P2 minus P1 is equal to gamma times Z2 minus Z1. And essentially all this says is that if I am going to offset my pressure somehow by moving up or down, then I have that change in pressure is offset by a change in elevation. Now, pressure and elevation are not one-to-one, right? They're not the same units. And that's where the gamma comes in, because ultimately what we do is divide both sides by gamma, and now we're saying P2 over gamma minus P1 over gamma is equal to Z2 minus Z1, right? If I just divide through by that. So in other words, that looks like this. So P1 over gamma plus Z1 is equal to P2 over gamma plus Z2. This is hydrostatics, and it just says that, remember that in a hydrostatic situation, nothing is moving. So if we are a small parcel of water, and we simply are moved for some reason from a shallow depth of, say, 1 foot below the surface in a swimming pool, and we go down to 5 feet below the surface in a swimming pool, but then we stay still, then the pressure has to change. It increases, and it increases just enough that when we divide that by gamma, we have the exact same change that we had in elevation, in the number of meters or feet, whatever our length unit is. So what this also tells us is P over gamma plus Z is constant, that the pressure divided by our specific weight of our fluid plus whatever elevation we care about is constant, right? If I move up, then a change in pressure and a change in elevation offset each other. If I move down, same thing. So we have this constant value. And that's going to be really useful. And so what I wanted to spend the rest of today talking about is how that could be useful and start to think a little bit about true distributions in space. Finally,
Another question.
Yep.
So we use this equation when the fluid is static. But like, let's say, for example, if it was a dam, like the water itself isn't moving, but like the particles in the water are moving. Does that make a difference?
The molecules themselves will be interacting with each other. They are vibrating. But overall, we are not seeing a net movement of water up or down. Now, the reality of we are idealizing the situation because when you heat up a surface and cool it in a reservoir, you can have vertical mixing and so forth. So we're not, or winds, that kind of thing. We are assuming that we are just staying static at the moment. So we are idealizing. Okay. All right. So let's get into a couple of clicker questions here back to back. What you're going to look for is, Lily Jin, I don't know if I answered your question. Sorry, that was from a few minutes ago. But I'm hoping that the further going through more of this means that got figured out. Okay, great. All right. So remember that you need to connect with the new version of the class through Reef or iClicker, and it is now called 2021 CVEN 3313 Theoretical Fluid Mechanics. So I think if you just search, it looked like from the chat, if you just search 2021 CVEN, you should come up with it. It should come up in a list. So hopefully that works. All right. I will start let me get I need to pull up the Reef app. It's hidden behind my PowerPoint here. But take a look at this. Get rid of that here. All right, these are 3 different shaped vessels, and they each have this sort of bluish green fluid in them, and they are all filled to the same height. That's what I'm trying to indicate with the the dashed black line. So the question is, which of these containers has the greatest hydrostatic pressure at their base? So on the bottom, right? We have different amounts of fluids of this greenish fluid in each of these. The question is, which of them, which of the A, B, or C, which one will have the greatest pressure at the bottom? So let me get this going. And by the way, I'm not going to show you the results of this poll. We'll see how pure pressure goes. We're apparently counting up. My bad. All right. So it's open now. And D, by the way, is the option that they're just all equal. So when I show you the solution here, I'll make those squares go away, and you should be able to see. I'm a little bit afraid that we only have 30 seconds. So I think that was the default, count up in 30 seconds. So we're at 5 seconds left. 4, 3, 2, 1. Hopefully everybody got it in. Oh no, it's still going. Okay. I'll stop it at a minute because that's been my plan, is to keep it at a minute. All right. We're up to 95 responses, so that's good. We've got another 15 seconds. 96 responses, that might be our fill. That sounds pretty good. Seems like that's most of the class. 98. 5 more seconds. 99. I'll give you a couple more seconds here because I think if I rerun it, everybody has to answer again. I don't want to cause that necessarily. 106, I'll give you another 10 seconds. All right, so we've got A, B, C, or D are the 3 options. So far, I'll show you the results in a moment, but nobody has chosen E, so that's good. And we'll end now. Okay. Ooh, there was a little jockeying there. All right, a few people changed their answers. Oh, come on. All right, so here are the results. 36% of you, or 36 of you, that works out with 100 people, said vessel A. Nobody said B. That's interesting. 8 of you said C, and 56 said D. They're all equal. Okay. The answer in this case is actually D. It doesn't matter how you have the water or in this case, the fluid, I guess I should say, because it's, I don't know, we don't know what it is. It's probably water with food coloring in it, but it doesn't matter how you have it distributed in an XY sense. The fact that they all have the same elevation or same free surface above the base of them means that they should all have exactly the same hydrostatic pressure at their base. And to prove that, let me move this out of the way. We're going to bring it back on the next slide, so I don't want to go back into presentation mode, but I should be able to. Oh, phooey. Sorry, that means, so let me just grab these and move them because we're not going to animate through them if I'm not in presentation mode. So let's move these, and if you can see that, all of these are at about the same pressure. Okay, so that's supposed to be proof that indeed these all have the same hydrostatic pressure at the bottom of them, despite having different amounts of fluid, but all having the same height in each of these 3 containers. All right, so that's a really, really important, aspect here. Sorry, I'm just checking the chats real quick. So volume does not matter with hydrostatic pressure. No, it's really about height and specific weight. And that's because it comes back to this. Oh, shoot. It's 2. Because it comes back down to P1 being equal to P2 plus a difference in delta Z, or another way to say that is this way. So it's just about where you are, how much water is there or fluid is there, liquid, and its specific weight. That's what it comes down to.
Professor,
Yeah.
a couple slides ago, you were talking about how specific weight is a constant and it's non-zero for the fluid.
Mhm.
So, doesn't pressure change the density of the fluid? So wouldn't specific weight be a function of Z?
I don't, that's a good question. I don't think, so liquids are going to be a continuum. So assuming that there's no change in chemistry or whatever, let's just, use the ideal case. In the case of hydrostatic pressure, the answer I believe is no, simply because the energy that the molecules have to interact with each other hasn't changed because there's more above them. There's more of them above them, right? So deep, I'm trying not to use something like deep in the sea because there are probably differences between shallow ocean water and deep ocean water. But if the sea was filled with just water without any other chemistry to it, I don't believe that these would actually have a different density to them. And therefore, I think your question was specific weight exactly, precisely. So I don't think either of those would be the case. In any event, for the purposes of what we're doing here, they won't be different, at least for the work you're doing in this class. Hope that satisfies you a little bit.
Yeah, that's perfect. Thanks.
Great. Okay, let's do the next one real quick. So Emmy asked, so all three of these would have the same pressure at the surface as well? Yes, they do. So at the free surface, at the very top, these all have, and we'll talk about this a little bit more on Tuesday, these all are open to the atmosphere. Now, and because they're all the same height, they're all the same, the free surfaces are all at the same elevation, they all have, the one way I like to think about this is they all have the same amount of atmosphere pushing down on them, okay? Now, this makes a difference if we are in Boulder, Colorado at, 5,400 feet above sea level, we have less atmosphere pushing down on us than if we were in San Diego, California, right at the coast. Then there's another 5,000 feet, 5,400 feet of atmosphere that can be piled up above us. So those two would have different, what we call atmospheric pressures at their surface. But in this case, these are all right next to each other. So they should have the same kind of weather over them and everything. But they also, because they have the exact same elevation, they will have the same pressure at the surface of their top surfaces as well. Terrific. Okay, so let's go to the next clicker question. All right, so this one is a little bit different, and we only have three options here. And the three options are, given three holes in this container, which one will generate a stream or jet that goes farther than the other two? So I will reveal what these look like after we're done, but let me start the poll now. We'll let it count up and take a look at responses here. The question is A, B, or C. We have some, again, atmospheric pressure pushing down up at the top. You could think about this in a couple of different ways. If you were swimming around in here, would you have, more or less pressure at these different locations? That sort of thing. And we're going to assume, by the way, that A, B, and C, the holes, those sort of like triangles, they're actually called jets in this case, they're like manifolds. But in any event, we're going to assume they're all the same. There's nothing. This isn't a trick question about them being different sizes or something. This is just to say if all of them were the same, if A, B, and C, the holes out to the atmosphere were the same, which one would have the greatest stream that would go further than the other two? All right, we're at 91 responses. There were 100 of you earlier, so let's see. So if you can't see the question in the Reef app, it's because I don't have this question programmed into Reef. So hopefully you're just getting the opportunity to submit something generic. And that's all I'm looking for right now is just a generic response because we're doing this somewhat interactively. Okay, if that We're up to 96. I'll give you guys another 10 seconds here. See what we get. Okay. Here are the results. Love it that happens. Okay, here we go. So we have 7 people voted for A, 2 for B, and 87, overwhelmingly, it looks like C. Now, let's see. I don't want to suppose why anybody would have chosen the other 2, but let me just say something about the layout of these 3, and then I'll reveal the solution here. As we go down, one of the things that we've said so far is that as we go down through the fluid and there's more above us, we have a higher pressure, right? Pressure has to increase because elevation is decreasing. That's another way to think about the hydrostatic equation. Pressure has to increase when elevation decreases, and then the opposite is true, right? When pressure decreases, that is because we are moving up in elevation. All right, so here's the solution. The one that goes the furthest here, these 3 nozzles, is C. So you guys are doing pretty well here. You've got most of you are on the right track, and the reason for that is simply that you're starting at a much higher pressure, pushing water out into the atmosphere at C than you are at B or at A. All right. All right. Let's get rid of this. I'm going to end that for today. Okay. Okay. Now let me get back into presentation mode here. Let's take a sec. Okay. So let's see if I can get rid of this guy. Okay. So the last thing that we ended with the other day was that there's a pressure increase with depth that will hold for fluid elements in place. And so we said that the sum of the forces in the vertical direction equals 0. That gave us F1 acting upward, F2 acting downward, weight acting downward. The sum of those equals 0. And what that meant was that F1 minus F2 was equal to P1A from the bottom minus P2A coming down from above. And the A's were the same, so we could pull those out and say that the difference in these forces is equal to A times P1 minus P2. And essentially what that allows us to do, because of the hydrostatic equation we wrote on the previous slide before we got to these clicker questions, is to really replace this P1 minus P2 by gamma times H. H is simply the difference between location number 1, the elevation of location number 1, and the elevation of location number 2. So H here is a thickness in this case, and it is the difference or the distance between these 2 faces. All right. So because of that, we have some pressure difference between point number 1 and point number 2, and we multiply by gamma, the specific weight, to get to this difference in forces. What this then means also is now we can add in the weight piece, right? This was just F1 minus F2. So we just took the first 2 pieces of this. The third piece of this is the weight is equal to gamma, the specific weight of the fluid, multiplied by H times A, right? And so all we've done is basically put W on the other side and made it equivalent to this. And then we just regrouped. So F1 minus F2 minus W, F1 is acting upwards, W and F2 are acting downwards, is equal to A times gamma H, which is this guy right here coming in, minus gamma times H times A. And what we end up with is basically the forces all end up at 0. This is different and a little bit nuanced than what we did a few slides ago before we got to the clicker questions, because those were about pressure. This is about force. So the forces have to balance here. The pressures over some distance in depth change. Okay, and that's why we ended up with non-zero on one side. The force balance will tell us that, but the force balance has to end up equaling zero. All right. Okay, so let's talk a little bit about pressure below a free surface. So here's a free surface where the pressure in the atmosphere is what we have at the very surface. And then we have some location that's H down from the open from the surface here. And here's our indicator that we have a free surface. Sometimes we also show like what looks like kind of a reflection underneath it. I'm actually used to that being opposite. It's like small to big, but in any event, this is meant to look like a reflection. So this looks more like a free surface. And the pressure at this point, we say that P1 in general, P1 is equal to P2 plus gamma times H. So in other words, we could say here that P at this location underneath the surface, the pressure at that point is equal to the pressure that's coming down from above, from the atmosphere. And this is a pressure we don't really feel, right? Like when you're sitting around, you don't feel the air kind of pushing down on you. But there is a true pressure that is there. In fact, it's like 101,000 pascals or newtons per square meter. That's at sea level. Okay, so the pressure then at this depth, it can be represented as the atmospheric pressure plus gamma times H. Gamma being obviously the specific weight of this fluid, but we multiply that by H to just figure out how much of this pressure is acting to give us this difference, right? Between the P atmospheric and pressure at depth. All right, let's put this to use. At the beginning of the lecture today, I showed you Glen Canyon Dam. Now let's talk a little bit about Hoover Dam. So Hoover Dam backs up Lake Mead, whereas Glen Canyon Dam backs up Lake Powell. And between them is the Grand Canyon. The Colorado River connects these two and flows out of Lake Powell through Glen Canyon Dam, then through the Grand Canyon, and then into Lake Mead here. Now, the Grand Canyon, the Colorado River, you can barely see it snaking through on the right here, but this is where it pops into Lake Mead. And you can see that Lake Mead, so the dam is right in here, I believe, but you can see that we're backing up water quite some ways, right? We have these two arms that are sort of getting inundated by having the dam in place. And you can also see this is not very far from Las Vegas. Las Vegas is a growing city that has relied on Lake Mead for quite some time for both a water source and for power generation. Now, for those of you who aren't aware, just a very quick aside, the Colorado River obviously starts here on the western slope in Colorado, so you've got to go over the Continental Divide. And the interesting thing about it, though, is that even in Boulder, we have water that comes from the headwaters of the Colorado River. Technically, the Colorado River starts at a number of small headwater catchments on or watersheds on the other side of the divide. But the sort of official source we consider to be right outside of Rocky Mountain National Park on the west side of the divide. There is, when the Colorado River then comes into this complex of reservoirs and lakes, Lake Granby and Grand Lake, and there is a pipeline that actually pushes water from that lake, from that side of the divide, over to Estes Park, and then that gets transferred down to Boulder Reservoir, actually. So there is West Slope water that comes over to the East Slope, and that water will never touch Lake Mead. I mean, I guess it could if I filled some up and took it in a jug with me and poured it into Lake Mead. But from a natural perspective, if we use it in our taps or we use it to irrigate fields or whatever we do with it here in Boulder, that distribution means that because we're on the other side of the Continental Divide, it will likely flow to the Atlantic Ocean as opposed to the Pacific Ocean, which is what the Colorado River was supposed to do. So there, within the state of Colorado, if you're not from the state, there is the physical divide of the Continental Divide is also a very big divide in interests with respect to both sides want the water, but they want it for different things. There's a lot of population on the eastern slope or the Denver Front Range area, Boulder and so forth. There's less population on the west slope, but that's where a lot of agriculture is done. And that's where there's a feeling that on this side, it melted on this side, it went into the rivers on this side of the divide. Why are you taking it away from us? We should be able to use it. But let's go downstream. The Colorado River then cuts through 6 other states. And so we have upper basin and lower basin states. And we have within the Colorado River Basin, we have Utah, Wyoming, Colorado, Arizona, New Mexico, Nevada, and California. So the river technically goes through all of these states, and they all have different claims to how much water they're allowed to take from the river. In fact, Colorado has not, and same with Wyoming, has not used all of their allocation. Part of the challenge with Wyoming is what are you going to do with it? There's just not the land to irrigate and sort of the right climate to irrigate with a lot of that. But in any event, we're now heading into more drought. And so these lakes these reservoirs are falling. In fact, we're, I think, going to be at about 50%, less than 50% of capacity in Lake Powell come this summer even after the next snowmelt. But anyway, that's a little bit of context. And that's part of the reason why these are so important. These 2 big reservoirs, Lake Mead and Lake Powell, end up being like a savings account. That is, for all the river water that comes down, these are places to store it to use at a different time. We don't necessarily need to irrigate a whole lot in, June when we've got snowmelt runoff occurring. We really need that water in August. And so we save it up in these reservoirs to use for any other time. But we also do a lot of power production. And so from these big dams, we get quite a bit of energy for the southwestern United States. All right. Let's move back to more of the physics here, more of the fluid mechanics. All right, so this is Hoover Dam now. And by the way, it wouldn't be, it's a little hard to tell these two apart. The one difference, I guess I would say, and now it's actually harder to tell, this is when there's a bridge that's now here. You can kind of see one end and the other. There's a bridge that's in place here now, but it is more recent than the one that was in front of Lake Powell. So a lot of the pictures in Glen Canyon Dam have that dam or the bridge in front of it. And now the new ones for Mead or for Hoover Dam now have this bridge in front of it now too. But you can see it's a little hillier and you don't get to see as much off in the distance. But in any event, here are some technical specifications for the Hoover Dam. It is made of concrete. Its height is 221.3 meters. The crest length, so across the crest here, 379.2. It's 13 meters wide at the very top, so that means from front to back. But the base width is 201.2 meters, so down at the bottom. So it's probably more or less flat on the upstream side, and then it kind of bulges out down river towards the other side to go from a top width of 13 meters to a bottom width of just over 200. So quite large. It backs up Lake Mead, and the reservoir capacity is 35.12 cubic kilometers. That doesn't sound like much, but it's quite a bit of water. And when it comes to acre feet, which is a unit we think of as covering an acre of someone's land to 1 foot depth, it's quite a bit of acre feet, hundreds of thousands. All right. Let's ask a question. Relative to the atmospheric pressure at the surface of the reservoir, so we're going to say in addition to that, what is the pressure at the bottom of the dam? All right. So for this question, we're going to assume that the reservoir is completely full. So we're just going to use 221.3 meters. That's kind of the biggest pressure we could have, right, down at the bottom. Otherwise, we're spilling water over the top. So let's just so right now we're not at a condition where we have it this deep, but let's just use that number as kind of a worst case scenario. We have used this equation or stated this equation a few times now. The pressure at some point within the water column now is going to be equal to the pressure at the surface plus the hydrostatic pressure as we move down through the water column. So that is gamma, the specific weight of water, times the depth, in this case H, the depth of water that we're at. So in this case, we want the pressure at 221.3 meters. That's the only substitution I've made here now is equal to the atmospheric pressure plus this gamma H. And when we say relative to the surface, that means that we can set the atmospheric pressure in this equation to 0. Because we just want to say, what is our added pressure? Like if we're at the surface, we're already experiencing that pressure of the atmosphere. So now when we go down, how does it increase from there? So we're going to use that as sort of a 0 or a reference point. All right. So we're going to set that to 0. And now we can simplify this equation even more, right? We say, we're going to calculate the pressure on the left-hand side. The right-hand side, this H is basically 221.3 meters, right? The total height of the dam. So we're going to plug that in for H on the right-hand side, and we're going to plug in the specific weight of water. So we have P, the pressure at 221.3 meters depth is equal to gamma times 221.3 meters. Gamma, we're going to take to be 9810. We don't have any information about temperature, so I'm just going to kind of use a standard value. 9,810 newtons per cubic meter for water. You can get that from the tables in your book, or you could look it up somewhere on the internet. This is kind of a standard value at 4 degrees C. And then we're going to substitute that in. So the pressure here at this depth is 9810, which is already a big number, multiplied by another fairly big number, 221.3 meters. Now, before I even do this math, I'm just going to look at my units. And I note that I have a force per volume, so force per length cubed, and I'm going to multiply it by a length. And it just so happens that I have both of these in the same units. So meters will cancel with meters cubed to give me meters squared. And I will get a force per area, which is exactly what a pressure should be. So just if I was concerned, I could at least do that quick unit analysis / dimension analysis. In this case, I've already turned the dimensions into units. But I could go through that and just make sure that I'm on the right path. So this comes out to 2.17 times 10 to the 6 newtons per meter squared, or newtons per meter squared is also known as a Pascal. So we could write this as 2.17 times 10 to the 6 pascals. All right. Is that a useful number? Like, I'm not sure what a Pascal is. I kind of know what a PSI is, like pounds per square inch. And I know that because I've inflated a lot of things in my life, right? I've inflated bicycle tires. I've inflated rafts. I've inflated balloons. I guess with a balloon, I don't know how many PSI I put in. But when I inflate the tires on my car, I know roughly where I should be. And I have enough of a modern car to tell me when I go low, right? When I get too low. So this seems like a big number, but it's hard for me to kind of wrap my head around. So let's think about some ways that we can just try to make this a little more useful. How much pressure is this? How much is 2.17 times 10 to the 6 pascals? Well, earlier I told you that, just as an aside, atmospheric pressure at sea level is 1.01 times 10 to the 6 pascals. And so 2.17 times 10 to the 6 is a little more than twice that, right? So if we took atmospheric pressure and it was 101.01 times 10 to the 6 pascals before we went under the water at Hoover Dam, we would go from sort of having only 1 times 10 to the 6 above us to having 3 times 10 to the 6 above us, right? Just by adding 1 plus the 2 to get there. So this is like having 2 more atmospheres worth of pressure added. Well, geez, you might be thinking, yeah, but I don't really feel that pressure anyway. Like, I don't feel the pressure of the atmosphere pushing down on us. All right. So the other thing then is we could convert it to PSI. And the reason I might do this is just that, again, I know that a tire on my car should be around 30, 35 PSI. That's kind of, depending on the vehicle you have, the tires and all that. And when I do this conversion, so I just looked up this conversion in the tables that you have in the back of the electronic book, and it said 1.45 times 10 to the minus 4 PSI is 1 Pascal. So I arranged this so that my Pascals are on top here. They're going to cancel because this is in the denominator, and then I'd end up with PSI. So now I have 315. Oh, well, 315 sounds like a lot because I know that the tire pressure for my automobile should be 30 to 35. So this is like about 10 times that, right? On the order of 10 times as much pressure as I put in my tire. And I know that if I pop my tire, I will hear a loud bang and have, quite a bit of air coming out. So this might just be a better way of just thinking about how much pressure 221.3 meters of water is above the bottom of that dam. Okay. Now, here's another question that I want to ask you. We know, or I guess I haven't told you yet, but we looked at the map and you saw the two long sort of fingers or arms, I guess, of this reservoir going out. It turns out that the longest of those two is 115 miles. All right. So I apologize for having meters and miles in here, but this was something I came across. I'm like, 115 miles. That's a long way, isn't it? I mean, that's what makes up all of the volume back there, right? That and the depth. Okay, well, that seems pretty impressive. Ultimately, what's happening then, what we've calculated is that at the bottom of this dam, we go from atmospheric or from relative to atmospheric, we start at 0 and we increase linearly our pressure as we go down. We're only talking about pressure. So pressure increases as we go down, and we get to, I forgot the number real quick, 315 PSI by the time we get down to the bottom, or pounds per square inch. All right, that's pretty impressive. Now, does it matter that I have 115 miles of water behind the dam? What if I only had 50 miles? Would it be the same pressure distribution? What if I had 1 mile? Would it be the same pressure distribution? What if I changed from 115 miles to 115 inches? Would I still have the same pressure distribution? And the answer is yes. It does not matter how far back you are storing water. Hydrostatic pressure distribution does not care about the X and the Y. It only cares about Z, the vertical direction. So whether it's 115 miles or 115 inches, you would have to build the same large feature and engineer it to hold back the same forces, essentially, or in this case, we haven't gotten to forces, but the same pressures, right? And so these two sets of arrows are essentially equivalent. Now they're equivalent because I've copied them and pasted them, so they are identical. But they're numerically, if we calculated them, they would be identical because nowhere in our pressure calculation to get to 315 psi down at the bottom of the dam did we ever care about how much water was extended behind the dam. We just cared about the height of that water. Okay. So that's a really important aspect to understand. Now, from an efficiency perspective, of course, you'd rather have 115 miles of water behind the dam than 115 inches, because that's a much more efficient way of spending lots of money and building a very large reservoir just to store water, right? 115 inches would not store that much compared to 115 miles. But either way, you would need the same dam in place to take care of the pressures and the forces. All right, so let's go back to this and just, we know that there are 115 miles. The pressure distribution then is, we started out with P at some depth, right, below the free surface is equal to P atmospheric plus gamma times H. So what's the slope of those pressure arrows? And what I mean is specifically, what is that slope right there, that dashed black line that I've put in? What's the slope of that? One way to look at P atmospheric plus gamma times H is to say that we are looking at Y equals mx plus b, where x in this case is some other factor that we care about. So the slope of this, P atmospheric to dp, it's not quite, it is dp, but dp, as it turns out, is equal to this guy right here. This exact slope comes out to be proportional to gamma. Gamma is what's controlling here. And this is going to be linear for starters, and it will be linear because of the way that gamma changes. Now, in our case with water, that was 9810. If we use the Hoover Dam to back up motor oil, that would be a very different, it'd be a mess, but it would be a very different gamma that we would use. And so we would have a different pressure at the bottom, and we would have a different slope to get down there. It would still be linear, though. That's what's key. It would still be linear. So dp dz is equal to minus gamma. And we started with that back on the, I don't know, second slide or something we talked about today, second or third. So dp dz is equal to minus gamma, meaning that as height changes, as elevation changes, the pressure change that goes along with that is gamma. So in this case, it's the same magnitude, right? But obviously we are increasing pressure as we go down. And the reason that this negative value is here is that dp dz is going to be a negative value. We could say minus dp dz is equal to gamma, but it's because z will decrease while pressure increases. So there has to be a negative somewhere in this equation. All right, so a real quick summary then on pressure variations in static fluids. We said that del P, del X, the pressure variation in the X direction, the pressure variation in the Y direction, when we think of X, Y, and Z as three kind of cardinal directions, both of those are equal to zero. The horizontal plane, fluids do not care, they're at the same pressure. So pressures do not vary in horizontal plane. There's no resulting motion of our cube of fluid that we had spent some time talking about. We also said that in the vertical direction, the change in pressure with elevation is equal to minus gamma. So the specific weight of the fluid is what is dictating this relationship. Therefore, we can say that P1, or pressure at some location, is equal to pressure at another location plus gamma times the height difference between those two locations. That's key. So pressure increases with depth, and the difference in pressure is offset by weight. Finally, there's no resulting motion, again, of our cube, which is key, okay? All right, it looks like I have gotten done about 11 minutes early. So homework number 3 should now be live and viewable in